well, since it doesn't appear anyone else is coming, let's go ahead and get going with these lectures. For the folks at home, I am sorry for that delay. Let me see something real quick. All right, everybody's up on Zoom. Go. Share screen. Let's go back. All right, picking up where we left off last class. We were talking about this idea of the chain rule. The chain rule really just relates rates, right? We say we've got this function with another function inside. We want to know what this derivative is, or what the derivative of this composition of functions is. And what the chain rule does is it says, well, we know how y changes with respect to u, and we know how u changes with respect to x. So using this, we're going to create a system of related rates. Let's say, all right, y changes with respect to u like this. Y prime is equal to f of u, right? F prime of u. But really all this is d du of f of u, right? So this tells us how y changes with respect to u. Now, u changes with respect to x in a similar way. So we know how y changes with respect to u, and we know how u changes with respect to x. What the chain rule says is to figure out how y changes with respect to x, well, that's going to be d dx of f composed with g of x. This is equal to f prime of u times g prime of x. Now it's important to remember that u is equal to g of x. And it's important to remember that because what we're saying is you take the derivative of the outside, not do anything to the inside. Then you multiply that by the derivative of the inside. Cool? So this is essentially what the chain rule tells us. It tells us how the change in y relates to the change in x. If we think about what we've got here, it kind of makes some sense, right? This is the change in y with respect to u. This is the change in u with respect to x. Come over here Y changes with respect to U in a particular way. U changes with respect to X in a particular way. So those changes in U's cancel out, right? And what we get is the change in Y with respect to the change in U. Another way to write this so in some sense, we can think of these DUs as having canceled because they represent the change in U, right? So really, this is just a daisy chain of rates that are related to each other. Folks at home, you can hear me, right?
Yeah, we can.
Awesome. Sweet. So, moving along, skipping some of this stuff because we've already talked about it. We had already seen that problem. All right, so one of the first things we can apply this to is the power rule. We've already seen the simple power rule, but more generally, if we have something like some function of x raised to the nth power, we want to know how that's going to behave. We can also think of this as u raised to the nth power, right? Where u is a function of x. So, looking at the more general chain rule, we've got dy dx is equal to dy over du times du over dx. Well, if y is a function of u that's equal to u to the n, so what I'm saying is, given y is equal to u to the n, and u is equal to some function of x, then dy du is going to be equal to n times u to the n minus 1 and du dx is just going to be the derivative of g. And that's all we're really saying here. Everybody cool with this? So to apply this really quick, let's say we've got y is equal to 1 over x to the third power. First, what's u? U is going to be 1 over x, right? So that tells us that y is equal to u to the third power. Agreed? So what's du dx? This is going to end up being negative 1 over x squared, right? Agreed. And dy du, well, that's the derivative of u to the third, right? So this, by the power rule, is just going to be 3u squared. This is dy du. So dy dx is going to be dy du times du dx. But we just found that dy du is equal to 3u squared, and du dx is equal to negative 1 over x squared. Everybody agree? But at the very beginning, we said u was equal to 1 over x. So now we have to plug that in here. That's 3 times 1 over x, that quantity squared, times negative 1 over x squared, so this is going to be 3 over x squared, right? Because we're just squaring the 1 over x. 1 squared is 1, x squared is x squared. So 3 over x squared times negative 1 over x squared, or negative 3 over x to the fourth. Pretty straightforward, right? And it's broken down like this. The first step is identifying the interior and working your way out. What is your most interior function? Then take the composition of functions outside of that. Having said that, notice in this particular problem, we could have gone ahead and applied the power rule if we distributed that power all the way through. So y equal to 1 over x, that quantity to the third. Well, that's just going to be equal to 1 over x to the third, right? And this is equal to x to the negative third. So we could have gone ahead and applied the power rule straight to this. Let's do that just to verify our answer down here. We're going to bring that power down, negative 3, x to the negative 3 minus 1, or negative 3, x to the negative fourth, right? Which is going to come out to be negative 3 over x to the fourth. So it's the exact same answer. Two different methods, exact same answer though. This was done with chain rule. This was done with the general power rule, right? What's up?
I had one
I
question
mean, the simple power rule.
on the middle portion. So with, I I know how you get the u, and I get the 3u. So when you pull out that 3, does the power that's above it, does it always go to the next one?
The next lowest,
Yeah,
yes.
what is that called again?
So that is the simple power rule.
Simple power rule. Okay, I was trying to remember what the name of it was.
I'm gonna go ahead and erase this here.
Sorry, I was just trying to remember what it was called.
So our book calls it the simple power rule. I have, except in this book, never actually seen it referred to as the simple power rule, just as the power rule. So we've got y is equal to x to the n. Then dy dx is equal to d dx of x to the n, which is equal to n times x to the n minus 1. And this is the rule we used.
Okay, I just was trying to remember what it was called.
Just a simple power rule. Having said that, we can actually kind of see how these two rules are the same. Let's set u equal to x here. Du dx would be equal to dx over dx then, right? So how does x change with respect to itself? Just 1, it's the identity. So this would be 1 times n times x to the n minus 1 then. So it's the exact same rule when we set u equal to x. Makes sense what I mean? And this brings us to the general power rule more properly. Given that u is a function of x, and you raise u to a power, let's call that power n, and let's say y is equal to that composition. In that case, the derivative of y is going to be the simple power rule applied to u raised to the n times the derivative of u with respect to x. Cool?
So is that what that little dash means?
Yes. That prime, that just means derivative. And you're going to see me use it a lot every now and then. A lot every now and then. You're going to see me use it a lot. I'm going to jump through a bunch of different forms of notation as we go throughout the semester. So as another example, we're given this function. We've got an interior function, 3x minus 2x squared, raised to a power. So we've got a u, that's just what our interior function is, right? 3x minus 2x squared. And we've got a y equal to u to the third. Applying the chain rule, I'm going to write everything out here on the board now. So we got y is equal to 3x minus 2x squared raised to the third. Let's set u equal to what's inside. And that tells us that y is equal to u cubed so taking dy du, this is going to be d du of u cubed. This is going to be 3 times u squared now looking at du dx. That's going to be the derivative of 3x minus 2x, that quantity squared with respect to x. So this is going to come out to be 3 minus 4x Now we want to know how y changes with respect to x. Well, we know how y changes with respect to u, and we know how u changes with respect to x. Putting this all together, we've got 3u squared times the quantity 3 minus 4x. Well, what was u? U, we said, was this thing over here, right? So this is 3 times 3x minus 2x squared, that quantity squared, times 3 minus 4x. And when we distribute that 3 to there, we get exactly what they have down here. Is everybody cool with this? Yep. Cool. All right. So here, this is going to take a little bit more crunching on. And I say that because we've got a lot of stuff going on inside, right? Now I'm going to make a suggestion that reduces this problem significantly. Once I get this board erased, I will show you what that suggestion is. We really need self-erasing boards. Engineering department, get on that. That's money. All right. So first thing we're going to do, rewrite everything, right? Y is equal to the cubed root of x squared plus 4, that quantity squared. Now we can rewrite this as the quantity x squared plus 4, that thing squared, all raised to the 1 over 3, right? Because anytime we see something like this, this is equal to u to the 1 over n, right? Now, we're also going to use another property a thing raised to a power, raise all that to a power is equal to that thing raised to the powers multiplied together. So coming over here, we've got x squared plus 4 raised to 2 over 3. Now, let's find our u as a function of x. Now, I would say u is equal to x squared plus 4. Which would make y equal to u to the 2 over 3. Everybody cool with this? So dy du is equal to d du of u to the 2/3, which is equal to 2 over 3 u to the negative 1/3. Yeah. Now, du dx, that's d dx of x squared plus 4. This is going to be equal to just 2x. So dy dx, well, that's going to be equal to dy du times du dx. That's equal to 2 over 3 u to the negative 1/3 times 2x plugging this all together now. 2 multiplied with that 2 is going to give us 4 over 3. U we said was equal to x squared plus 4 raised to the negative 1/3 power times x. And we could write this in a more reduced form if we wanted to, but so for right now, let's just leave it as it is. Okay, so this gives us dy du. Now the question asks for the tangent line of the graph when x is equal to 2. So we got the general equation to find the slope with. Now we're going to have to actually find the slope. So at x equal to 2, n is equal to 4 over 3 times 2 squared plus 4 raised to the negative 1 over 3 times 2, right? So this is going to be equal to 8 over 3 times 4 plus 4 is going to give us 8. The negative 1/3 power. Now I'm going to bring this over because I'm out of room. Eight over 3 times 8 to the negative 1/3 power. This is equal to going to be equal to 8 over 3 times 1 over the cubed root of 8, which is equal to 8 over 3 times 1/2, or just 4 over 3, right? All right, so this gives us our slope of the tangent line. Now we need to find our y value. At x equal to 2, y is equal to the cubed root of the quantity 2 squared plus 4, that quantity squared. So this is going to be the cubed root of 8 squared. Well, couldn't we reverse the order of our roots and of our power? Couldn't we do like this? This thing is equal to 8 to the 2 over 3, which is equal to 8 squared, my mistake, 8 to the 1/3 squared. That's a valid rule, right? So doing that, this is going to come out to be 2 squared, or just 4. So y is equal to 4. Now, you've got to put it all together in slope-intercept form. I mean, in a point-slope form to get slope-intercept form. We have y minus 4 is equal to 4 over 3 times x minus 2. Well, this whole thing comes out to be 4 over 3 times x minus 8 over 3. Adding 4 to both sides, y is equal to 4 over 3 times x minus 8 over 3 plus 4. Well, we can rewrite this 4 as 12 over 3. So 4 over 3 x minus 8 over 3 plus 12 over 3. This tells us that y is equal to 4 over 3 x plus 4/3. Okay. Now, what did we just do? First, we used chain rule to find the derivative of this thing. Then we said, all right, we've got the derivative of this thing that we found here. Well, this is the general equation for slope of our tangent lines, right? So since we want to find the tangent line at x equal to 2, that means all we got to do is plug in 2 here. We've got the slope of the tangent line at that spot, right? So we did that. We found that the slope was equal to 4/3. All right, cool. Now we need to know what the y value is associated with x equal to 2, right? So we went ahead and plugged in x equal to 2 into our original equation and got 4 out of that. So the point we're looking at is 2, 4. The slope of the tangent line through our function at that point is going to be 4/3. So we've got everything we need now to throw together point slope formula. That's what this is. This is the y value when x is equal to 2. This is the slope when x is equal to 2, which we found from the derivative. And this is just x equal to 2, right? So we said, all right, cool, we've got point slope form. Now we want that in slope intercept form. Work through the algebra and reduce it down. Comparing our answer to here, theirs at the bottom left of the slide, comes out to be the same. Is everybody cool with this? Good. Awesome. Dope. So we could, well, for the second time, I'm just going to jump straight to the solution of the slide. Looking at example 5, we've got 2 problems, A and B. They can be tackled in a couple different ways. Notice A could just be tackled with the simple power rule, or my mistake, no, it can't. It can be tackled with the quotient rule or with the chain rule. B can only be tackled with the chain rule. So, looking at the solutions really quick, rewriting this, our interior function, u, would be equal to x squared plus 1. So that means y is equal to u raised to the negative first power. And that's what we're doing here. This is the derivative of y with respect to u times the derivative of u with respect to x, and we put everything back together. Similarly, part B. So as another point, we could reduce this problem a great deal for us. We could actually multiply this through to the interior, right? When we did, if we did, we would get x to the 4th minus x to the 6th, all raised to the 1/2 power. And that's what they're trying to get at here, is that first, rewrite your problem using powers. That generally is just a good rule. I mean, we saw it here, helping us simplify our problem a great deal, right? Because otherwise we're gonna have u is equal to x squared plus 4, s is equal to u squared, and y is equal to s, the cubed root of s, I mean, right? Like, we would have had 3 steps in that. But by turning it back into powers, we've simplified it a lot. And that's what their point is here. So here, we're going to apply the product rule. Then we're going to say, hey, this thing requires chain rule. This thing, nothing other than the simple power rule. Make sense? What else did I want to go through? So a quotient raised to a power, we could go ahead and distribute that power all the way through. Sometimes that's a good idea, sometimes it's not. If we don't, then here we could just apply the chain rule directly, right? And that's the point of this problem, is to say, you could either distribute that power all the way through, in which case you would get the quantity 3x minus 1 squared divided by the quantity x squared plus 3 squared. Or you could say, yeah, let's use the chain rule. This thing we're going to have to hit with the quotient rule no matter what. But at least I know dy du, it's going to be pretty quick and easy. So what I am saying is you can go about this one of 2 different ways. We could say y is equal to 3x minus 1 divided by x squared plus 3, that quantity squared. U is going to be equal to 3x minus 1 divided by x squared plus 3. So y then would be u squared or the other way we could go about this is to say, all right, since y is equal to 3x minus 1 divided by x squared plus 3, this whole quantity squared, this thing's going to be 9x squared minus 6x plus 1 divided by, let me actually expand this out even more, 3x minus 1, that quantity squared divided by x squared plus 3, that quantity squared, is equal to 9x squared minus 6x plus 1 divided by x to the 4th plus 6x squared plus 9. And then apply the quotient rule. We could go either route. Here, the derivatives are going to be a little bit longer, aren't they? Here, not so much. So it's a matter of looking into the problem and seeing what you want to do with it. notice what they're doing is applying the chain rule and the quotient rule. Quotient rule gets applied to U, right? Chain rule gets applied to the whole thing. And in either case, your solution should come out this. Is everybody cool with this? Good. Okay. So a quick summary of everything we've done up to this point. We've got the constant rule, which says the derivative of a constant is 0. We've got the constant multiple rule, which just says if you're multiplying a thing by a constant and taking the derivative of all of that, just go ahead and pull that constant out. Take the derivative and then multiply the two back together. Sum and difference rule says the derivative of the sum of two functions is equal to the derivative of each function added together. The product rule says the derivative of function f and function g, in this case u and v, multiplied together is equal to u times the derivative of v plus v times the derivative of u. The quotient rule, low d high, high d low, divided by the square of what's below. Power rules, we've got two of them now. We've got the simple power rule, we have the general power rule. The general comes from the chain rule, which is dy dx is equal to dy du times du dx. So having said that, let's go ahead and take a quick break. Give you all about 10 minutes, do a little respite. Come back at 5 after 7.